اوكي، بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. I am Saddam Al-Azzani and I will be moderating today's session. Welcome all attendees and thank you very much for joining our today webinar. This webinar is organized by SDAIA-KFUPM Joint Research Center for Artificial Intelligence and facilitated by KICS. We have an interesting topic today entitled Fuel Design and Property Prediction Using Machine Learning. Our speaker today is Dr. Abdul Gani Abdul Jameel. Dr. Abdul Gani Abdul Jameel is an assistant professor in the Department of Chemical Engineering at King Fahd University of Petroleum and Minerals, and he is a fellow at SDAIA-KFUPM Joint Research Center for Artificial Intelligence. He did his PhD and postdoc at the Clean Composition Research Center at King Abdullah University of Science and Technology, KAUST. His research interests are in the domain of petroleum fuels for transportation and energy generation. He is primarily interested in using machine learning techniques for predicting fuel properties and designing fuels of the future. Dr. Abdul Ghani has published over 40 papers in leading peer-reviewed journals in various research areas. Kindly be informed that all attendees will be muted throughout the presentation, and this session will be recorded automatically by the admin. You can type in your questions in the question box, which will be answered at the end of the presentation. You can also raise your hand and ask your question directly. Dr. Abdul Ghani, please go ahead. The floor is yours.
Thank you, Dr. Saddam, for your nice introduction. And thank you all for attending today's talk. Let me share my screen. Dr. Saddam, can you please confirm if you can?
Yes.
Thank you. Today I will be talking about fuels and AI. There is a lot of hype and euphoria around AI for the past decade or so. I think AI has been, especially in chemical engineering, it has been there for a few decades. It has been applied for a variety of different problems in process control, especially in fuels as well. But these days, because of the increased computational power, we are now trying to truly use the ability of AI for solving a lot of problems. And today we will be talking about how we can use AI for predicting fuel properties and also designing fuels using AI. So first of all, I would like to ask this question. What is the need for AI in fuels? Just because AI is there in every other field, what is the need for it? I'd like to give you guys an example. Now, when you go to your gasoline station here in the kingdom, you have gasoline 91 and gasoline 95. The 91 refers to the octane number of the fuel. Okay, it is the 91 is the octane number of gasoline. You can think about octane number as the quality of the gasoline. Now imagine, now you are, let's say for example, you are mixing 91 gasoline and 95 gasoline equal parts. And let's say for example, you want to predict what is the octane number of the gasoline mixture. Now, if these fuels mix linearly, then I think we can say that the octane number of the mixture is 93. But the problem is the fuels properties, when they blend, when they mix non-linearly. Okay, so it could be anywhere between 91 and 95. So we can understand that. But there are some variety of fuels, especially the oxygenated fuels. When you mix them, the octane number is beyond 91 and 95. Now that is very strange. Okay, for example, you mix equal parts of 91 gasoline and 95 gasoline, you expect something between 91 and 95. But for certain fuel categories, it's beyond 91. And sometimes it's even 100, sometimes it's 80. And this is something that it's very, that is because of the complicated fuel chemistry. Okay, and this is something that normal linear techniques cannot predict. So that's the reason why our first interest was towards AI. If we can somehow use AI and try to predict this strange behavior of the fuel. Now, for simple fuels, which have very less complicated chemistry, we use linear regression models like multiple linear regression and partial least squares. These very much do our prediction job. But when you have something called as synergistic and antagonistic fuels, that is when you add two fuels, sometimes they tend to enhance each other's capabilities, and sometimes they tend to cancel out each other's capabilities. I'm using the word capabilities just because the audience is, I don't want to use complicated terms. So in a synergistic fuel, they tend to complement each other and increase the properties beyond each other's original properties. So now, and the opposite for antagonistic fuels, they tend to destroy each other's properties and go lower than each other's properties. That's why we need something like machine learning, which can capture these properties from fuels. And then when you have a newer fuel, and when you try to predict the properties of a new fuel, the idea is these machine learning models will be able to predict these properties of the synergistic and antagonistic fuels in a very good manner. Now, before I go more detail, I want to ask this question: what are fuels? What a fuel is like a cocktail. A cocktail we have for juices. We mix a lot of juices. A fuel is also like a cocktail, but instead it's a cocktail of molecules. There are various different types of molecules. Now, if you take gasoline, for example, we do a detailed hydrocarbon analysis for gasoline, and if you do this, you'll see that gasoline has approximately 200 to 300 different types of molecules. And if you were to do a DHA for diesel, you will see that diesel has thousands of different molecules. And in fact, if you take one drop of crude oil, and if you see, you will find millions and millions of different molecules. I mean, on the face of this earth, there is nothing more complicated than crude oil. I mean, crude oil is the most complicated mixture, according to me, on earth. Okay, because if you take one drop of crude oil, you will just find thousands, you'll find millions of different molecules. So this is what a fuel is. A fuel is just a real fuel that you see, that you put in your car, in your diesel engine, is just a bunch of different molecules. Now, the idea is, we have this question: can I predict the property of a fuel from its molecular information? Now, this is a general question that I, as a PhD student, I had in my head. Now, from the molecular structure or the chemical composition, can I predict the properties of the fuel, like octane number for gasoline or cetane number for diesel and so on? Now, let's assume that we can do this. Let's assume that we can predict the properties of any fuel from knowledge of its molecular information or chemical composition. The problem is, the fuels are too many. The molecules in a real fuel are just too many. And even if you somehow do find out what are the different molecules and what is the percentage of each molecule, we have a lot of information, and that information is just too much for us to process. And because the information is just too much, it becomes difficult to process, and it also becomes a little difficult for us to actually use them. Now, for gasolines are simpler compared to diesel and heavy fuels or kerosene. For gasoline, we can find to some extent the different molecules in the fuel, but for diesel and more complicated fuels, even with the today's state-of-the-art technologies, we cannot break them down into their constituent molecules. So now the question is, how do we understand the composition of the fuel if we cannot even see the molecules? And then how do we predict the properties? Now that's another second challenge. The one way to deal this problem is, you see all of these bunch of different molecules which we cannot find out. Now, if you take gasoline, for example, it has like few hundred molecules, but if you break them down into functional groups, for example, you see all these colored pictures, right? The colored, each color represents a single functional group. A gasoline may have a few hundred molecules, but these few hundred molecules are in turn made up of a small number of building blocks, okay, or skeletons that I call as functional group, okay. For example, if you take, let's say, for example, ethane, for example, ethane has 2 methyl groups. Those who know some chemistry, okay. And for example, if you take N-heptane, for example, N-heptane, if we go back in our school, we remember the straight chain carbon, and it has 7 carbons, and the 2 carbons at the very edge are methyl groups, and the one in between are CH2 groups. So these are functional groups. Now, it's possible for us to know these, to find out these functional groups in the fuel. Okay, so now a fuel which has hundreds of molecules, you can break its composition in terms of functional groups, and the number of functional groups in a fuel are very less, like 7 or 8. You can condense the information of the fuel in terms of functional groups. A fuel which had thousands of different molecules, now you're breaking its composition in terms of functional groups. Now it's like 7 or 8 or 9 or 10 functional groups. This will make up like 95% of the mass of the fuel. So now we can understand the chemical composition of the fuel in terms of the functional groups. For example, most of the gasoline and diesel, you can break them down into paraffinic CH3 groups, paraffinic CH2 groups, olefinic groups, naphthenic groups, aromatic groups, and so on. Okay. Now, we can identify them and quantify them using convenient methods. Okay. And this captures the fuel's composition. Each fuel has its own functional groups. Now, the next question is, how do we, from a chemistry point of view, how do you characterize the fuel in terms of the functional groups? Now, we have advanced techniques called as nuclear magnetic resonance spectroscopy. I won't go into too much details because we have varied audience. To keep it simple, NMR is a very advanced high resolution technique. And with this technique, you can identify, you can very accurately identify and quantify the various functional groups to a very good accuracy, and then you can distribute the fuel in terms of functional groups. Now, for example, this is the NMR spectra of a phase G standard gasoline. Okay, it's a standard gasoline called as phase G, and this is the NMR spectra, and each peak in the NMR spectra represents a functional group. And we have developed equations, mathematical equations that can convert the area under each peaks into the functional groups. Okay. Now this, from the NMR spectra, I can calculate the weight percentage of the functional groups. For example, this phase G gasoline has 23 weight percent aromatics, 33 weight percent of paraffinic CH3 groups, and so on. So now I have broken down the fuel into functional groups. Now the big question is, can I use the functional groups of the fuel to predict its properties? Remember, we said we want to predict the properties of the fuel, and we said that we want to use the molecular information, but then we said molecules are too many, we cannot identify them, but we can identify the functional groups. So now that we are able to identify the functional groups, can we use these functional groups of the fuel to predict their properties? The second question we want to answer is, what modeling techniques do we need? Do we need AI, or we don't need AI? Okay. Now, from our experience, as I said before, fuels, when they are mixed, when they blend with each other, they blend linearly, non-linearly, and also in a very complicated manner like antagonistically and synergistically. So for these reasons, when we tried going for linear techniques, our predictions were not good. But the moment we used advanced AI-based techniques, we got very good results. And that's the reason why we started using AI for our modeling approaches. So we are trying to predict the fuel properties from the functional groups using AI as our modeling technique. So this is the background of our work. And with this information, I'd like to give you the outline of the presentation, which is first I'll talk about octane number of gasoline and how we are going to predict it. What is the need to predict it, and then cetane number for diesel, and similarly soot formation. We want to predict the soot that is formed, all the carbon particles, and then we will talk about fuel design. So let's talk about the octane number of gasoline. First of all, what is octane number? I mean, if you look at your textbook definition, talks about anti-knock properties and so on, but I'll try to keep the definition very simple for you. Let's call it as the quality of gasoline. Okay. Now people wonder, what type of gasoline should I use in my car? Should I use 91 or 95? Remember, every car engine is made for a fuel. If you have an engine that is designed to go fast, then you should be using 95, because 95 will give you a high octane number. It can withstand high compression, so it will give you a lot of power. So you will use 95. If your car is not designed for that a very high load, then it's better off to use 91. So that's there. Now there are different types of octane numbers. Okay, let's call it as research octane number and motor octane number. This is the fuel property, but these fuel properties are measured. It can be measured at different conditions. Okay, so these are two standard methods. Now, when you go to your petrol station, the 91 that you see there, right, 91 or 95, it is the average of the research octane number and the motor octane number. The research octane number is like when you're driving slowly, and motor octane number is like when you're driving fast on the highway. Okay, so we take the average, and that average number is posted on your gas station. Now, for example, any refinery that sends out a gasoline, it has to experimentally measure the octane number for each batch and prove it's 91 or 95, and only then you have to send it out. So to measure the octane number, it's very expensive. Trust me, you need millions of dollars worth of equipments, and you need very skilled. I mean, this is a very if to measure the octane number, you need an operator who is highly skilled, and there's a lot of other chemicals involved in measuring the octane number. It's very time consuming, and especially when you have a high throughput lab where you have to measure multiple samples, then do experimental measurement becomes very expensive and very time consuming. Now, because of these things, there is a need to, can we predict instead of experimental measurement, can we predict the octane number of a fuel from the chemical composition very accurately, so that it can match with the experimental values? If we can do this, then we will minimize a lot of the cost and time. That is the motivation behind the study. So now your refineries, instead of spending so much time on measuring the octane number of single batch, multiple batches can be measured in a matter of minutes. That is the idea. Now, how do we do this? Now, first of all, I said research octane number and motor octane number, there are two different octane numbers. Okay. Now we experimentally measured some of these octane numbers, and some we collected from literature for a different number of fuels. Okay. And and then we did, for example, the NMR experiments to know what is the functional group of these fuels. And then we made a data set with all the fuels functional groups on one side, and the RON, which is the octane number, the research octane number, and the motor octane number on one side. And then we try to predict and now we are going to use this data, the data of 281 fuels. Now, buried within these fuels is the mathematical relationship between the functional groups and the octane number. Now, we want to understand what is this mathematical relationship, capture it, and then use it for new fuels. That is the idea. So we need some mathematical technique that can read or try to understand this relationship. And we try to do for linear programs like multiple linear regression, and our accuracy of prediction was not so good. So we went for machine learning based methods. And we used, there are a lot of machine learning algorithms out there. But I'm going to talk about them a little bit later. But we used artificial neural networks because it has higher accuracy than others. Now, I said we have to build a data set. A data set is what? It's the fuels. We should know the inputs. The inputs is the functional groups and the output. The output is the target, which is your octane number. So we have 281 fuels in our data set. And I just want to show what those fuels are. They are pure compounds, mixture of pure compounds, and even real fuels. For real fuels, we did NMR experiments to get the functional groups. So this is just for your information that we have a large data set, and embedded within this data set is the relationship between functional groups and octane number. Now, how do we capture this data? How do we capture this relationship? Now, basically, our is a supervised learning technique. So we have a lot of raw data with us, okay? And we train this data using there are a lot of algorithms like neural networks, random forest, SVM. There are a lot of methods out there. And in fact, if somebody is very new to machine learning, I would recommend you guys to maybe go to YouTube. There's a lot of information there which you can learn by yourself. What is machine learning, or what are the different training algorithms, and there is a step-by-step way. So we have to train the data, and from the trained data, and there is a lot of way to train the data. It's very complicated, and there are a lot of steps involved in training the data. Maybe I'll try to touch a few of those. But then after you train the data, and after you get a satisfactory model, and then when you have a new fuel, you feed in the functional groups of the new fuel, and it will give you the octane number of the new fuel. So that is the idea. Now, this algorithm that you see here, we use artificial neural networks. And artificial neural networks are machine learning algorithms. Now you have like the basic architecture of an ANN is like, it has an input layer. Your input layer here is the inputs to the model. In our case, it is the functional groups. Then you have some hidden layers. Your hidden layers are the computational nodes inside the model, okay? And then you have an output layer. An output layer is your target that you're trying to predict. In the present case, it is the octane number. Now, as I said, this is the architecture that we used. So we have, for inputs, we have functional groups, and you can have one hidden layer or you can have two hidden layers. You have to keep changing things until you have the you develop a model which is accurate enough for you. So we did a lot of changing things, and we found two hidden layers to give us the good performance of the final model. Now we used there are, for those who are like very new with those who want to develop supervised models, simple ANN models, I would recommend you to use MATLAB. Now MATLAB has inbuilt tools where you can upload the data using Excel, and you can make a model within a few hours. There is no programming involved if you use MATLAB, but you cannot do a lot of changes. You cannot change too many architecture. You have to stick with what you have in MATLAB. But we used Keras using leverage on top of Google TensorFlow. So that now you can write some codes, and you can change the architecture of the model the way you want. Now we did a grid search, and a grid search is basically how you can make the model in many different ways. Okay, even today there is no exact science on how you build a model. You can play around with things until you get your accurate model. So if you don't understand some of these terms, then I suggest you go back to the literature and learn, because it's now, if I cannot explain each and everything in detail because it's out of the scope of the presentation. So we in our final model we had two hidden layers. You know, our loss function is called as mean percentage error. We make a model and see how good or bad the model is, and we use mean percentage error. You know, when you train the data, we train the data with a batch of 16 data points at one time, and we use 5,000 epochs. Epochs is like we train the model with our data set 5,000 times. Okay, we continuously train the data 5,000 times. That is called as epochs. And then, you know, we have something called as we have to when you give the data set. Let's say, for example, a data set has 100 points. Usually, a percentage of the data is taken and kept aside, maybe 15%, 20% for testing of the model. And the remaining 80% is used to develop the model. And in this 80%, the model, you know, we have something called a k-fold cross-validation. Your training data set is broken down into k folds. So imagine, for example, 80% of data, let's say if you make it into eight groups, the model is trained on 7 groups and it is validated on the 8th group. In the second step, it is developed on the other 7 and validated on the other one. So this is called a k-fold cross validation. So this, even when you have small data sets, this is a very good technique to increase the accuracy of the model. And then for each layer, we have different units, and then we use something called as dropout. This is a regularization technique where we reduce the overfitting of the model. Sometimes the models tend to memorize the data, which leads to overfitting. We want to reduce the overfitting, and we use dropout. That is, a dropout technique is very useful these days, and it tends to drop out some of the nodes in the hidden layers. So we have like 0.14 nodes were dropped out in the first hidden layer and 4% in the second hidden layer. So let's talk to the final results. We developed a final model, and we tested the model with 20% of the data set. So approximately 40 experimental points were kept aside. They were not used to train the model. And these 40 points were then, you know, the model was tested on these 40 points. And you see the predicted octane number, the predicted research octane number, and the measured octane number. You can see that the model does a very good job in predicting the octane number of new fuels. And the average absolute error is 1.2. And this is like very close to the experimental uncertainty of octane number measurement. So if you were to measure the octane number for a fuel and then do it again, you'll not get the same value. It might be slightly different. There is an experimental uncertainty. So our model is giving very close to the experimental uncertainty. The experimental uncertainty is about 0.5. So using a modeling technique, we have brought this to 1.2. So you are now, the predicted value is very close to the experimental uncertainties. We developed this model, and we also deployed this model on this Cloudflame infrastructure developed by KAUST. So if anybody has like a fuel with the functional groups or just pure components or blends, you can go to cloudflame.kaust.edu.sa and you can enter your numbers, and it'll give you the octane number, and it'll predict your research octane number and motor octane number. So this model is developed, published, and also deployed. The second thing we'll talk about is the cetane number. Just like octane number for gasoline, we also have cetane number for diesel. I won't go into too much of details. Cetane number is, you can talk about, it gives the ignition quality of diesels. And you have cetane number, you also have something called as derived cetane number. They are functionally equivalent. It's how you measure them in different techniques. Now, as I said before, experimental measurement is very expensive and time consuming, and we want to bring in a prediction technique which is very simple, very less expensive, and you can can measure a lot, you can predict the properties of large amount of fuels in a very quick time. We wanted to increase the complexity when we went for diesel. So we added alcohols and ethers. Alcohols and ethers are not normally present in crude oil. They are added to diesel as an additive. Okay, so now we are able to measure, we are able to predict the cetane number of real fuels with additives as well. Okay, so now this, you take any diesel out there, we can give you the, we can predict the cetane number to a very good accuracy. That was the idea. What is the methodology? The methodology is something very similar to what we did for gasoline. The first step involves, we have to collect, experimentally measure the cetane number for a large number of fuels, and get some data from the literature. Okay, so we collect, we generate some in-house data, and we also take data from the literature. Okay, but we only take those data that are measured, in the standard technique, so that there is no issue with the experimental, because when you do an experiment and I do an experiment, there is always an experimental bias. But we try to stick with ASTM standards so that the data is as accurate as possible. And then after we got the data, we measured the NMR spectra for some of the real fuels so that we can find the functional groups. And for the case of cetane number for diesel, we had a very large data set. We have like 516 fuel. This is like exhaustive. It's like more than what we need. So now we have this is a very good data set, and now this data set has built-in information to predict the cetane number of any diesel out there. So it is rich in information, and this information is taken out. This mathematical relationship between the functional groups and the cetane number is extracted by the machine learning techniques. And we also used the artificial neural networks again as our machine learning algorithm. We tried different other methods, but we always found neural networks to be more accurate than other training algorithms. So as I said, we have 516 different classes of diesels, and I just want to show what our data set comprises. We have pure components, and even in pure components, we have alcohols, we have ethers, we have paraffins, we have olefins, we have a distribution of all. If our data set is lacking, let's say, for example, if there are very few ethers or very few alcohols, then when you have an ether-based or alcohol-based fuel, and when you try to predict the property of these fuels, the model will not do very well. So your data set has to be very good. It has to be diverse. Only when your data set is diverse, only then you will be able to predict accurately the properties of diverse fuels. So I think we've developed a very diverse data set of 500 fuels. Remember, these 516 fuels are 516 experimental measurements. Imagine how much work was gone into this. 516 points, like 516 experimental measurements. This is like millions of dollars of money and time spent. So that much data has been extracted from the literature, and we also did some for our own cost. So now we can use this data to make future experiments easier. Now we also, as I said, I also developed a multiple linear regression model. Okay, so like for example, we have the cetane number on our DCNSD derived cetane number here, and we try to develop from the data set. We try to develop a linear relationship between the functional groups and the cetane number, and the accuracy of prediction was not very high. So we have a bunch of constants, and you can do this from Microsoft Excel. You just need a data set, and you can do this multiple linear regression in your Microsoft Excel. And we did this. We did this for simple fuels. When we did for simple fuels, when there was no alcohol, there was no ether, the prediction was good. I mean, it's something that we can live with. But the moment when we introduced alcohols and ethers, these fuels which have complicated chemistry, which have antagonistic and synergistic properties, then the linear regression failed. It was not able to give accurate prediction for these complex fuels with complex chemistry. Now we have to go with more advanced methods, which is we went for machine learning using neural networks. And now we have to develop the model. And as I said, how you how you develop your ANN architecture. I still say it's not a science, it's trial and error, whatever gives you. I think the methodology of developing the model is still a little bit black box. There is no particular technique or a guided technique. I recently saw one of my friends in Aramco. He developed a technique to help the user, guide the user to build the ANN models. So he's trying to patent this. So there is some work going on to find some rules on how to make the model. Presently, it's a black box. You have to play around, try trial and error, and what gives you the best. So we used, we found 2 hidden layers. It gave us a very good prediction, and we used mean percentage error as our loss function. We use 32 batch size. When we feed 32 data points to the model at once, and we found 3,000 epochs. That means we trained the model with 3,000 times. We fed the model 3,000 times the data set, which gave us the model, the accurate model. So, and then when we develop this final model, remember we have to, during the training phase, we have 3 sets. One is the training set, which is like usually 70% of the data set. 15% is the validation set. The remaining 15 is the test set. The test set is taken and kept separately. It is not, it never comes in contact with the model. And then when the final model is developed, when we think, okay, the accuracy is very good, the performance is very good, then we test this 15% data with the developed model. And when we see that this new model, this model is able to predict very well on unseen data, then we can say that this is a generalized model that will work for any unknown fuel. I think for our model, we got, because we had a large data set, and we saw that our average absolute error is 0.91. Remember, the experimental uncertainty is 0.5 for the same fuel. If you measure now, you will get maybe 40 cetane number. If you measure again, you'll get 40.5. Okay, this is an experimental uncertainty. Now, from our model, we are able to get the absolute error is 0.91, which is very good, and I think we are coming very close. In fact, soon I think we will match with the experimental uncertainties, and I think our models will become very accurate, so that it can simply replace the experimental measurements by law. So we are going towards that. These models are still being used, but then, you know, with a pinch of salt. But then that time is slightly going away, where real time adoption is very close, in my opinion. So our final model is able to predict the cetane number of pure compounds, blends, real fuels, even with oxygenates and ether additives. Okay, so this is like people usually build models for pure compounds, but we've come a lot further than that. So we are now we're trying to predict the properties of the real world fuels. So any diesel out there, you bring it, we can test it. We can predict the properties. So even this model is also deployed on the same Cloudflame infrastructure. So we usually, when I see in research, people try to develop models, and those models sit in somewhere, and they are never really used. So it defeats the entire purpose. So we wanted to bring, we said no, we are going to bring our models out to the real world, so that we get a lot of traffic. So people come to our to these sites and try to enter the data. So there is like a interface between the model, and we have a web page where these deployed. So if somebody wants to predict your cetane number for any fuel, you can go on to Cloud Flame and you can predict the properties of the diesel as well. The next thing I'm going to talk about is soot. I'm not going to take a lot of time about this. I mean, soot is the carbonaceous. For example, if you burn any fuel, for example, let's say, for example, you are burning in a kerosene lamp. I mean, when you're small, we saw kerosene lamps. When from the flame, you'll see all these carbonaceous particles. So this is the soot. And even in your car engine, if you see at the exhaust, you see a lot of carbon particles, which are the soot, which is soot. And this is very dangerous for our health. And depends on the size, it can even be carcinogenic. So now when refineries are trying to formulate fuels, we're not only trying to target the octane number or cetane number. We also want to make sure that these fall into they are also very clean. That is, they will burn and their soot emissions will not be very high. Okay, so we also want to make sure that. So we also want to predict the sooting propensity. What I call it. What is the propensity of the fuel to form soot? So we want to predict that as well. So we also made a data set where we found we have a system here, a smoke point measuring system with which we measure a lot of different fuels, and we measure the sooting of each fuel. We have approximately more than 300 fuels in our sooting data set. So we have the fuels and the sooting propensity, which I called as threshold sooting index. This is one parameter where you can measure where you can quantify what is the sooting propensity of the fuel. Higher the TSI number, that means your fuel is going to soot a lot. It's going to give out a lot of carbon particles, which we don't want. We want to reduce it. So now, while you are predicting the octane number and the cetane number, you can also predict the sooting index of the fuel. And we followed the similar approach. I am not trying to, not giving out the data. So we also built out a model, and the model gave us like, we tested the model with 15% of test data, and it gave us good results. And apart from this octane number, cetane number, and so sooting, which I said, we also developed models for flash point. We've developed models for smoke point. We've developed models for viscosity, density, enthalpy of combustion, and we are in process to develop models for laminar flame velocity, surface tension, and other few properties as well. The final thing I want to talk about is the fuel design. Okay. Now, instead of predicting the property of a fuel, how about I design a fuel with the target already in hand? Let's say, for example, I have 3 or 4 fuels with me, and I want to mix these fuels in an order so that I get a gasoline with 95. Now, how do I mix these 5-6 fuels? There are many ways to do this. Okay. So what is the way to do this? Now, we've developed a system with which you can predict, or you can actually design or even screen fuels for their octane numbers or cetane numbers. Now, to talk about this design, I'll just give you some insight on what happens in the refinery. So in a refinery, your crude oil goes into your distillation column, where it goes into gasoline, naphtha, kerosene, fuel oil, and goes into a lot of distillates and residues. Sometimes these residues are taken and they are treated again in isomerization units, in FC cracking units, in reforming units, and then at the very end, when you make gasoline, see, gasoline is actually blended. It's not like you take gasoline, the crude oil distillation will give you gasoline, you sell it. No, gasoline is like in a recipe. It is blended, usually blended with whatever you have. Now, just like you when you make coffee, you put water, you put the coffee powder, and you put sugar and whatever it is, you put milk. The same way we make gasoline from different, whatever is available, maybe 4 or 5 streams. Maybe we take an FCC stream or isomerization stream, and then we mix all these distillates to make the gasoline. Now, this blending is guided by the experience of the operator. And we also have some models, linear models that guides the operator to make it. Now we want to use our AI-based models to make this process more efficient, so that the blending of the refinery can be without any errors. The reason is to make it very simple. Now, when imagine you are the blender, you are blending, let's say gasoline 95. Now, there are two problems. One is, if you make, let's say, for example, 94 instead of 95, now you cannot sell it. You have to reblend it. And this reblending, right, this is very expensive. You have to take the entire batch, you have to mix it again. It involves a lot of time and a lot of money is wasted. So you cannot afford this. Another problem is quality giveaway. Now, instead of 95 octane number, let's say you make 96 or 97. Now you are giving a better quality fuel for lower price, which is also not very good. Okay. So if you want 95 fuel, we just have to make 95 fuel. Okay. We cannot make 94 or 96. Both are a problem. In fact, if imagine, for example, for each 0.1 to change the 0.1 octane number, it costs 8 cents per barrel. And for 1 million metric tons, it costs around $670,000 to change 1 octane number, okay, for reblending it. So this is a lot of money which we can save if we make the right decision. And AI-based models can help us with those right decisions. So now what is our aim with the fuel design? Our aim is to design a fuel with a target in mind. It can be 91 or 95, based from a set of available streams. You have different available streams, 6 or 7 or whatever, with some additional constraints. Okay. Now you just cannot mix the fuel as you want. For example, there are always some regulations, like you need to add 5% of ethanol. That should be there as per law, or there should be 10% of aromatics minimum. So you have these additional constraints. So we are including these additional constraints into our model and trying to develop a design mechanism where we can design a fuel with the target while also satisfying the constraints based on regulation, even based on the season. When the season changes, your thing, there's a lot of changes. You need to make different fuels for different seasons. So you can keep playing with your models so that you can make the right blend. So how we did this, maybe I'll go a little bit fast so we can finish this in a few minutes. So we have 3 systems called the polygonal algorithm, genetic algorithms, and the ANN model. So we use these 3 as our integrated system to design the fuel. So we developed, all of the code was written in Python. Now, the polygonal algorithms, the purpose of these algorithms is to give a score. Now, for example, the way we did this was we assigned a score for each fuel. So basically, we want to use, for example, we have a fuel with a high octane number and a fuel with low octane number. When we mix it, we want to use the fuel with low octane number as low as possible. And we want to use the fuel with high octane number, which is expensive. We want to use that as low as possible. So we give a scoring. Higher the octane number, higher the scoring. Lower the octane number, lower the scoring. So we want to make sure that our blended product is also very cheap, not just technically right, but also very cheap. So we take care of this with the polygonal algorithm. So I have all these scores that we develop, and then we use genetic algorithms. Genetic algorithms are like search algorithms, okay? And they are, when you have like a search problem, we use the purpose of natural selection. For the purpose of these genetic algorithms is to generate the pool of mixtures. Various, you can mix 5 or 6 fuels in an infinitely number of ways to give you the design final product. So the purpose of the genetic algorithm is to generate these pools. So when we generate these pools, some pools will have good prediction, some will have bad. So then we use the best pools, and then we we develop their, it's called as parent or offspring. Some parents have a very good prediction, so we use their offspring and then we cancel out the others. Okay, so now we as we go one step another, we try to make our predictions better and better until we satisfy the final target. And the artificial neural networks is something that we already saw. We used our already developed model for gasoline octane number here. So it's already integrated. So it's like for the polygonal method, genetic algorithm, and the ANN, all the three are linked, are integrated into a system. And I think we discussed a lot about this, the ANN before. And in our model, we have functional groups, and our target is the octane number. So these are the different functional groups that we used. And I think we talked about the ANNs before. And we tried to validate this. I have skipped a lot of information. I didn't put there on purpose to make it simple. I just want to give out the message. So we tried to validate our system with a lot of different fuels. The word PRF is a primary reference fuel. TPRF is a toluene primary reference fuel. Binary fuels, multi-component fuels, and phase fuels. So whenever the system predicts a composition, we test that composition and to see if it works. Okay, and you can see that this is the predicted and the measured values for RON and MON. Okay, and you can see that the predicted values and the experimentally measured values for the stream is very close to the experimental values. In fact, the correlation coefficient for the octane, the research octane number and motor octane number is like 0.99, and the absolute error is approximately around 1.99 and 1.2. So this is like very close to your experimental values. So using this ANN, using our integrated structure, I think we can design fuels. We can accurately design fuels from a given set of input streams with additional constraints, and this can help any refinery to reduce the loss of quality material. It can prevent off-specification products. It can prevent quality giveaway. The mechanism, the system that we have, this system can also be updated towards other fuels, maybe for diesel or naphtha, and also for other properties like cetane number, and also for other properties like flash point, viscosity, density, and so on. So we are trying to do that at the moment. So basically, we're trying to use AI to solve these problems. We're trying to solve the problems that we see in fuels. So this is our work, and I would like to thank Dr. Motaz for his leadership in the center and for giving me the opportunity to give this webinar. And I would also like to thank Muhammad, my PhD student, and Faisal, my MS student, for developing these models, and also for Vincent from Delft University for collaborating with us and for helping us out on coding and on other aspects. So thank you very much. Your help is very well recognized and acknowledged. So I think we have 5 minutes, and I'm sorry I took a bit time. So if you have any questions, please.
Thank you, Dr. Abdul Ghani, for your interesting presentation. And now I will open the floor for the questions. Please, for those who have questions, please raise your hand or type in your question in the question box.
So I got a question from Hus Ali. The question is, can we use this approach to predict biofuels? Yes. In fact, what we used in our diesel, I said we used alcohols and ethers. So these alcohols and ethers, they are actually biofuels. Ethers and alcohols are usually derived from biosources. So yes, we can predict biofuels. Even, for example, if we are also working on developing models for biodiesel as well. Biodiesel has a different chemistry than regular, because we have a lot of methyl esters in biodiesel. So we are also trying to predict the property, the cetane number of biodiesel, which is different from the petroleum diesel that we have.
Here is a question from raise hand from the Dr. Abdul Malik Mohammed. Please, Dr. Abdul Malik, go ahead. Dr. Abdul Malik. Dr. Abdul Malik.
I think he typed this question here on the chat. He asked, what was the baseline metric as compared with the predicted result? Not exactly sure what is meant by baseline metric. So we usually, what was the baseline metric as compared with the, I don't understand the question. Maybe please send me an email. You can send me an email, or we can take it, talk about this, because I don't understand the question.
I think he means here what is the accepted accuracy or MAA or R square.
See, the R squared for any model is, it depends. Just some people say that I have a R squared of 0.99, so my model is very better than somebody who has a R squared of 0.98. That's definitely not the case. The R squared, the regression coefficient for the test set depends upon the test set itself. It depends upon the model, and it depends upon the training data set. Just by the R squared value, you cannot say the superiority or inferiority of any model. It has to be a qualitatively check of all the data and the testing. I hope if that was your question. Okay, we have more questions here from Roa. The question is, can we use different functional groups? What is the parameter used by the hidden layer? So I'll answer your first question. Can we use different functional group? Yes. So actually, a functional group is like just a part of the molecule. Okay. Now, for organic fuels, from hydrocarbon fuels based on aromatics, propane and alkanes, or paraffins, olefins, naphthenes, whatever functional group is available, we already took it. Okay. Additional functional groups is like esters, acids, ketones. These functional groups we did not use because they are not present in gasoline or diesel. Maybe if these are used as additives, then we will have to redevelop the model by including these functional groups. So until we have these complicated fuels, there is no need to go for these different functional groups. But if you want to combine 2 or 3 different functional groups and name it something else, then yes, you can still do that. You can use different functional groups. It's the way you see it. And the question about what is the parameter used by the hidden layer. See, these are the hidden layers have nodes. Okay, these nodes are mathematical numbers which have weights. It's a little difficult to explain this in person in limited time. I suggest you to look into some YouTube videos to understand what neural networks is, what is the hidden layer, what is the purpose of them, and what are the nodes, what are the weights associated with it, and what is dropout. It's a little complicated. So maybe I suggest you to watch some videos and maybe read some literature to answer this question. And the final question I see by Anonymous is, can you please teach us how to do ANN or simple method of machine learning in reaction class? Okay, this is one of my students. So he's asking me if I can teach ANN in the class. Sure, I would. Maybe we can do that. I also recommend you guys to take some of the machine learning based courses offered in the university. I know one course offered in petroleum engineering using AI. I would recommend you to take those courses so you can learn the theory behind it and also how you do it practically with a lot of projects. We can also do it in classes.
Okay, there is no more questions. At the end, I would like to thank all of you for attending our webinar presented by Dr. Abdul Gani and organized by SDAIA-KFUPM Joint Research Center for Artificial Intelligence, and looking forward to seeing you in our upcoming events.
Thank you, everyone.